So the next thing we are going to discuss in details is the very interesting subject of the satellites of Earth, which has a natural satellite, the Moon, with the time period of 27.3 days, which interestingly and very interestingly is also equal to the rotational period of the Moon about its own axis. Okay? The rotational period of the Earth about its own axis is 24 hours. But the rotational period of the Moon about its own axis is very close to this period, 27.3 days. And that is why we can see only one face of the Moon always. And we have been seeing it for time immemorial. Okay. Now then, whether it is the Moon or it is a man-made satellite, this is the Earth. Okay, this is the Earth. A spherical body we have taken the Earth to be of mass m and a radius capital R. The satellite is going around the Earth, okay, at a distance of r plus h from the center of the mass of the Earth and at a height h above the surface of the Earth. Okay. Now let us see, and let us say that v is the speed or velocity of the satellite. Okay. Angular velocity multiplied by r, that is the speed. Let's talk about the speed. Okay. Now the Earth and the body in motion, they have, this goes in a circular orbit in a plane only because there is a centripetal force which has to be there. Without the centripetal force, bodies cannot go round in circles with traveling equal distances in equal intervals of time. This is what happens in the case of the uniform circular motion, UCM. So this centripetal force which is required for the system is mathematically described as mv square upon r plus h, because the orbit has got a radius r plus h, mv square upon r plus h. And at that distance, there is a gravitational force on the satellite by the Earth, on the body by the Earth, and by the body on the Earth. And the magnitude of this force turns out to be equal to capital G mm upon r plus h square, because the formula is G m1 m2 upon small r square. Okay, same formula is applied. Naturally, what's the relation between this calculation and this calculation? The centripetal force is being provided by the gravitational force of the Earth on the body. We'll forget about the force that body puts on the Earth, because Earth is a very massive body and the body under motion, the satellite is a small body. So we'll not talk about that, because why I'm escaping that? I'm not talking about that, because the state of a body is determined by the forces acting on the body and not by the forces which the body exerts on other bodies. I told you this, I repeat, The state of a body is determined by the forces acting in the body. The superposition of the forces that act on the body. The state of a body is determined by the forces acting on the body and not by the forces the body exerts on other bodies. So what we do? We equate these two. Okay? mv square upon r plus h is equal to capital G mm upon r plus h whole square. 1 r plus h and another r plus h, they cancel out. Small m cancels out with small m, and we are left with the square of the velocity like this. V square is equal to capital G m upon r plus h. Now look at this equation. This equation tells us something. The equation tells us something loud. Okay, it speaks loud. And what is that? Look here, man. We will decrease if h is increased because the denominator becomes more and more. So the velocity with which the satellite is going to go in the orbit at higher heights will decrease. So bear in mind, v square is equal to 2gm r plus h. Okay. Now let us see if the satellite is close to the surface of the earth, maybe some kilometers from the surface of the earth. So what will happen? If h is equal to 0, then v square will be equal to gm upon r, because this h that we have taken here will be negligibly small, and therefore we can ignore that. So v square is equal to gm upon r. I'll multiply by r up and down, okay, and then we find that this is equal to capital Gm upon r square, and this capital Gm upon r square has been taken by us here as equal to small g, our familiar friendly small g, which we call the acceleration due to gravity, but I still insist that you call it the gravitational field close to the surface of the earth. Okay. Now let us see as to what distance this satellite is going to travel in each orbit. Okay, distance traveled in, so no, this is EATCH. Yeah, I'm sorry. Each orbit, not the Earth's orbit. Of course, it's the Earth's orbit. Orbit round Earth. So this is equal to 2 pi into r plus h, because for any circle, the circumference is equal to 2 pi into r. It's very simple. Of course, in meters, the speed is given in meter per second, capital V. So therefore, we can calculate the time period, okay, as 2 pi r plus h divided by V, okay, because it's basically, I'm writing the result very directly. I should have written that 2 pi r plus h, 2 pi r plus h, this divided by t will be equal to V. I will do it, I'll bring V here and t comes here, therefore t becomes equal to 2 pi r plus h divided by V, and this is the time period associated with the satellite. So we found that the time period of a satellite at a height h above the surface of the earth, that will turn out to be equal to its orbital path divided by its velocity. The velocity, which we found that the velocity square is equal to gm upon r plus h, okay, and therefore substituting the values 2 pi r plus h divided by under root of gm upon r plus h, okay, Now I can take this under root r plus h in the numerator, and I get 2 pi r plus h raised to the power of 3 by 2 and divided by g. Okay. So if I square this relation, then I get t square is equal to 4 pi square upon gn r plus h whole cube. And if I consider this quantity 4 pi square over gm, they are all constants, I take it as a constant, then I can write t square is equal to a constant times r plus h cube, which is the radius of the satellite's path, and the time period squared therefore is proportional to the cube of the radius of the path of the satellite around that. Now t squared proportional to r cube. This is basically Kepler's law of periods. Kepler gave us 3 laws. The first law is that all planets, they travel in elliptical orbits. The sun is situated at one of the 2 foci of the ellipse, and in fact they can come very close. When they overlap each other, then of course it is this thing. Okay. So Kepler's law of periods. If h is very, very small as compared to r negligibly small, or r we take h to be equal to 0, okay, then I get t square is equal to k r cube, because h turns out to be 0 over here. Okay, so I can write this as the square becomes, now k square I substitute here, 4 pi square over gm into r square into r cube I will split in 2 parts. So now this part gm upon r square, which goes up, this is actually our familiar friend from before, and that is the acceleration due to gravity near the surface of the earth, or what I call the field near the surface of the earth, gravitational field near the surface. So therefore in that case, where the satellite is close to the surface of the earth, if I write this time period for that particular satellite as t0, it will turn out to be equal to, I'll just take the under root in both the sides, and this is equal to 2 pi under root r over g. Okay, 2 pi under root r over g, and this will turn out to be equal to 2 pi 6400 kilometers 10 to the power of 3 divided by 9.8, and we arrive at a very magic number, and that is about 85 minutes, which incidentally matches another result for the same reasons, and that result just I am telling you what to do. If I have the earth, and if I dig through the earth a tunnel, and the earth is taken as having a uniform density throughout, and for that particular kind of thing, if I drop a mass here, then it comes here and comes back, and the entire period is also a matching 85 minutes like it has been obtained in this particular case. Okay, so I'll talk more things about it. So let us discuss the energy of an orbiting satellite, whether close to the surface of Earth or a geostationary satellite or whatever. So let us see that the kinetic energy of the satellite is equal to half mv square is equal to plus capital G m upon 2 r plus h. Okay. The potential energy at this distance r plus h is equal to minus capital G m upon r plus h. So the total energy of the satellite is equal to the potential energy plus the kinetic energy, and if I put the values, then capital G m upon 2 r plus h minus capital G m upon r plus h, which is 2 capital G m upon 2 r plus h, and therefore we find that the value turns out to be equal to minus times capital G m upon 2 r plus h, which of course is a negative value, and it has to be negative because the satellite is at a finite distance from the surface of the Earth. If not, then of course, and the satellite moves around because of the centripetal force provided by the gravitational pull of the Earth on the satellite. So it does not escape to infinity. Negative means does not escape to infinity. Okay. We'll talk next about geostationary satellites, weightlessness, and Kepler's laws visited properly in the next lecture. Okay, so till then I wait for your questions. I wish to get them, and I like to answer the questions if I know. Okay, thank you very much.